So what exactly is matter? Matter is mass. Matter is anything that takes up space. It's what everything that we know of, can see in the universe is made up of. It does occupy space and it does have a mass, and most of our matter is included in solids, liquids, and gases that we know about. Now, the forms of matter, the different ones have different properties. So, solids and liquids behave differently from gases, and then solids and liquids behave differently from each other as well. And all matter is known to have a set of properties, making that matter unique in and of itself. Okay, when we're talking about matter, matter has two different kinds of properties and changes. They are physical and chemical. Physical properties are things that can be observed without changing the substance, things like density, color, boiling point, melting point, things of that nature. When you have a physical change, you're just simply changing it. It's still the same thing, such as slicing a piece of bread or crushing a soda can. You still have bread and you still have a soda can, but you've just changed its shape, kind of. You've altered it, but it's still the same thing. Now, chemical properties describe how a substance reacts or how it changes into something else or how it's going to behave when in the presence of something else. Chemical changes can't be undone. You've changed it into something brand new. For example, fire. If you're burning something, you can't unburn something. Or if I bake a cake, it's not like I can unbake the cake afterwards. It's going through a change, and that's what a chemical change is. It gives us something new. Most matter is going to be made up of compounds of elements. However, some matter has only one kind of atom, and when it has only one kind of atom, those individual types of atoms are called elements. And each element is going to be different from every other element, and it can only be broken down to the size of about an atom. Anything smaller than that, and it will no longer be the element that we're talking about. Now, there's 92 naturally occurring elements out in nature, and only about 25 of them are essential for life. A lot of the other ones are going to be used for other things, but 25 are necessary for life to happen. Four of them, in fact, oxygen, carbon, hydrogen, and nitrogen, make up 96% of your body weight. So that's the bulk of what we're made of is carbon, oxygen, hydrogen, and nitrogen. Okay, pictured here is the periodic table of the elements. You're not going to have to memorize it for this class, but I do want you to be familiar with a little bit of it. First of all, it's called the periodic table because there are periods or rows, and those are our elements. That's how it's organized. But it also has some groups, and the groups are what go up and down. And that kind of tells us how the elements react. All of the elements in a group tend to behave the same way. There are a couple atoms of interest, or a couple elements of interest for us. They are carbon over here, nitrogen right next to it, oxygen over here, and then our hydrogen up here. Remember, we said that these four make 96% of our body weight, so those are the important ones we need for life. We'll learn about some of the other ones as well, but that's the basics of what I wanted you to know from the periodic table. Okay, when I combine two or more elements together, we form what we call a compound, and compounds are what we tend to find out in nature more than the individual elements on their own. Now, the property of a compound can be different from the elements that make them. In our example here, we're going to talk about water real quickly. Water is made of two elements. The first is hydrogen, and hydrogen is really flammable. It burns really, really well. It's explosive when it burns. The other element in water is oxygen here, and oxygen is required for things to burn. If you take the oxygen out of a fire, the fire stops burning. It needs to have that oxygen for fire to go. So if I take something really explosive and I add to it the ability to burn, I would have this huge explosion. And that's what happens when I mix hydrogen and oxygen together and give them a little spark. But then it forms water. And water is an amazing thing. As you know, water is not very flammable. In fact, that's what we use to fight fire. So you can see how the properties of water are different than the properties of the elements that make them. Okay, here's our real simple model of the atom. I wanted to show it to you so we can show the parts of the atom. The first part is the nucleus, and that's the center here of the atom. It's filled with two subatomic particles. We find the proton, which has a positive charge, and then the neutrons, which have no charge. And together, those two form the nucleus. Now, orbiting around the nucleus in electron clouds are where we find our electrons. Those are these guys here, and they follow around in these areas. And it's not a perfect circle. This is just a simple model, but the electrons have a negative charge. So the protons are positive and the electrons are negative. Also, the protons and neutrons are about the same size, while the electrons are teeny tiny in comparison to them. And that'll be important in the next slide. So if we go back to the periodic table and we take hydrogen, one of the elements we were talking about, And then we also remember our model that we had. What we do is there's a couple things we want you to know. First, here's the element name, and in this case it's hydrogen. And then we have the element symbol. And the symbol is going to be 1 or 2 and possibly 3 letters. Normally they're just 1 or 2. The first letter is always going to be capitalized, and every letter thereafter is going to be lowercase. So that's our symbol. Now, the most important thing here is this atomic number. That's how the periodic table is organized. It also tells us what element we have. And the atomic number is equal to the number of protons that we have, and that's the defining characteristic of an element. If the element is neutral, the atomic number is also equal to the number of electrons, but always, always, always it's going to be the number of protons. And then down here we have the atomic mass. And the atomic mass is equal to the number of protons plus the number of neutrons. And that's important because protons and neutrons have an atomic mass that's about equal, and then our electrons, like we said, are much smaller. They're going to be about 1/1800th the size of a proton. So they really are negligible, and we really don't count them. Okay, lastly, we're going to talk about ions and isotopes. Before we do that, I want to remind you about our friend, the proton. The proton has a positive charge. It's found in the nucleus, and it's the defining characteristic of an element. If we change the number of protons, we change which element we have. So that's not something we want to play around with. Now, we have ions. Ions involve changing the number of electrons. Okay, and remember electrons have a negative charge. So if I add electrons, I make a negative ion. If I take away electrons, I make a positive ion. And an ion, quite simply, is just an atom with a charge. And then lastly, we have our isotopes over here. And the isotopes are going to deal with the number of neutrons. Okay, and neutrons have no charge, so they don't affect that one. They're just going to determine whether it's a heavier version or a lighter version of the element. Now, our atomic mass, if you remember, was something like a decimal, and that decimal is because we take the average of all the isotopes. And some isotopes are useful. In the fact of carbon, most carbon is going to be carbon 12, which means it's going to have 6 protons and it's going to have 6 neutrons, and that's how we get this 12. But every once in a while we find carbon 14, and carbon 14 also has 6 protons because that's what says it's carbon, but this time it has 8 neutrons, and that's where we get the 14. And carbon 14 is radioactive, and we use that one for dating, but we'll get to meet him a little bit later on in the class. All right, thank you, and we'll see you in the next video. Okay, before we talk about our bonding patterns and our chemical reactions, I want to go review the atom with you real quickly. Here we have our simple model again. Notice in the middle we have our nucleus, and in there we have our protons. Okay, remember the proton has a positive charge. It's the defining characteristic of an element. So the number of protons tell me which element we have. In this case we have 11, and that tells me that I have sodium. So this is a model of a sodium atom. Orbiting around the nucleus is where we find our electrons. And remember, the electrons have a negative charge to them. They're also much smaller than the protons. And the ones that we're really concerned about are going to be the ones that are in the outermost ring. So this one right here is going to be the one that we're most concerned with. And that is because it's called a valence electron, and those are the ones that are involved in bonding. And we'll learn more about that in a little bit. Okay, so what is a chemical reaction? Quite simply, a chemical reaction is when we mix elements together to form a compound or something new. We're going to use a real simple example here. We have our reactants here in green, and the reactants are going to be mixed together. We're going to add a little bit of energy, and we're going to come up with our product over here. In this case, what we're doing is we're taking hydrogen gas and oxygen gas, and we met them a little earlier in the unit. We add a little bit of an explosion, and then we get a new compound, which is water over here. So our reaction can be several different ways. We can write it out as words, as you see down at the very bottom here, or we can use the element symbols to kind of show us a mathematical one. One thing I want to point out is when you see the arrow, that tells us it yields, and the arrow shows us the direction of the reaction, so the way that it's going. Sometimes you'll hear these also called as chemical equations, but for now we're just going to use them as a reaction statement. Okay, so the first bond we're going to talk about is the covalent bond. And in the covalent bond, the valence electrons are the outermost electrons. Remember, those are the ones that are involved in bonding. Those are going to be shared. So they share the electrons between the two atoms. In our example here, we're going to use water once again. and we have a hydrogen atom here and a hydrogen atom here, and then we have our oxygen atom, which is going to be right here. And we know it's that because if we look here in the nucleus with 8 protons, that tells me it's oxygen, and over here with 1 proton, we know that we have hydrogen. Now, hydrogen normally has 1 electron. Okay, so that we'll put a box around that 1 electron there, and we'll put a box around this one so we know which is which. Now, it has space for 2 electrons in its orbital, so it's going to look to borrow 1 of those electrons from oxygen, and that'll be this one here. And when they share like that, what we notice is that both the hydrogen atoms have 2 electrons now that can orbit around it. And that makes that a very happy atom, and it's very stable, and it likes to be that way. Now, oxygen is a little bit different. It has in its outermost shell 6 electrons, okay? And we can see the 6 ones in purple here, and it's missing 2. So by sharing 1 with hydrogen and having hydrogen share 1 back in both cases, it fills those empty holes, and we see that in this outermost ring for oxygen, it has its 8 electrons, and we'll learn that 8 is the magic number, and that makes that part very happy as well. So because both of the hydrogens and the oxygen, all 3 of them have their outermost shell filled because of the sharing, it makes it a very stable molecule, and water is such. So the big thing to remember in a covalent bond is that we have shared electrons, okay? The other type of bond we're going to talk about is an ionic bond. In an ionic bond, we form ions, and if you remember, ions are where we give or gain an electron, okay? So by giving away an electron, we become a positive ion. By gaining an electron, we become a negative ion. So here we go again, and we can find our sodium ion here. We know it's sodium because it has the 11 protons. And notice that it has this 1 single solitary electron, 1 valence electron in its outermost shell. If we take a peek real quickly at chlorine, chlorine has 17 protons, so normally it has 17 electrons, and the last orbital here has 7 of them. Okay, so under normal circumstances, it has 1 empty space. So what happens is this sodium ion has only 1 in its outermost shell, and if it can get rid of that one, then this outermost shell doesn't really have to have any in it, and the next one is going to be full. That's this one here, and that'll give it its 8, and it'll be a happy atom. Remember, the magic number was 8, and you'll learn a lot about that in our lessons, so I'm not going to go into it too much here. But with our chlorine, it had 7 in the outermost one, and if it gains 1, it gets to its magical number of 8, and it'll be happy that way. The net result, however, is that my sodium ion now has a net positive charge, and my chlorine atom is going to have a net negative charge. And in nature, one of the real cool things is opposites attract. So the attraction between this positive charge and this negative charge is what keeps sodium chloride or salt together. So just to review real quickly, I want you to remember we had 2 types of bonds. We have covalent, okay, and in a covalent bond we share the electrons. And then we have the ionic bonds, and in the ionic bonds we give them or gain them. Okay, so we give away electrons, we form ions. And those are the 2 bonds that we'll talk about in the lessons, and those are the primary ones. Okay, we'll see you in the next video. Okay, so let's start by talking about chemical formulas. A chemical formula is a shorthand way of telling you what's in that chemical, or what that is that we're looking at. So let's do a real simple example first, and we'll look at water. Now you could simply, every time you wanted to talk about it, write out water, but we can also do its chemical formula using its symbols and some subscripts. The first element that's in there is hydrogen, and we have 2 of them, and the H is our symbol for hydrogen, and that little subscript, this one down here, tells me that there's 2 atoms of hydrogen here. And then the final part of our formula is going to be to add in that oxygen, and that's going to be this one here. So our formula is H2O, and what it does is it tells me that I have 2 hydrogens and 1 oxygen. Now if we look at the other molecule, this one over here, we see that it's a little bit larger and there's a couple more things attached to it. If we notice, there's some big blue molecules. If we were to count them, that's going to be carbon, and there's going to be 6 of them. Then if we look around, we'll notice these little black orbs here, that's what our hydrogen is going to be this time, and it's going to be 12 of them. And then finally we have our oxygens here, and there's going to be 6 of them. So this molecule right here has a formula of C6H12O6, and that tells me it's a sugar, and in fact this one here is glucose, and we'll be talking an awful lot about that one as our year progresses. Now sometimes you're going to hear the term radicals come up every once in a while. What a radical is that's when you have a group of atoms that are bonded together, and they like to be bonded together, and they behave as their own individual group. So they'll stay together throughout a chemical reaction. One of the more common ones is this one right here, this OH that you see down at the bottom. That is our hydroxide, okay, and that's an OH. It has a negative charge to it. And here it's paired up with barium. So we have BaOH, barium hydroxide, and then this little subscript 2. And remember that subscript 2 tells me that I have 2 hydroxides attached to the 1 barium here, so it looks this way. Some other common ones you can see over here. We have sulfate, the SO4, chlorate, chlorine, and 3 oxygens, nitrate, a nitrogen and 3 oxygens, carbonate, a carbon and 3 oxygens, and finally phosphate, which is a phosphorus and 4 oxygens. And these ones here, when you see these written in an equation, they'll generally behave as a group and they'll stick together. Okay, let's take a look at naming real quickly. The easiest ones to name are what we call our binary compounds. And what the binary tells me is that there are 2 atoms is all. Okay, so we'll have 2 different elements is all that there's going to be there. And when we're naming them, there's 2 simple rules. The first part is we take the name of the first element in the compound. So if we look down at our example here, our first element is going to be barium. So that's going to be the first part of our name. The second name in a binary compound is the second element, but then we change the ending to this IDE. So if we have barium plus oxygen, we make barium oxide down here. And you can see in the chart here that for a lot of them, you can see how we change. And it's just that second name, we just change it a little bit. So chlorine goes to chloride, iodine goes to iodide, bromine goes to bromide, and oxygen, like we saw, went to oxide. So pretty easy to name a binary compound. You take the first element, call it just what it is, and then you add the second one and add the IDE, the I to it. So what happens if I have more than 2 elements here? Well, that's where it gets a little bit confusing. If you remember back to our discussion, we talked about those special groups, the radicals. They can make it easy. If we take a look over here, we have our molecule here. Remember the little subscript tells me that I have 3 of these groups attached to it. So this one here is pretty easy to name. We take the first element here, and that would be aluminum. And then we add this radical name, and if you remember, that was the hydroxide. So we have aluminum hydroxide would be the name of this one. We're not going to go into a whole bunch of this. The reason being is you'll do this in chemistry. So just wanted to show you that we can have different names. And remember, we saw our big guy earlier, our C6H12O6. Now, to name that would be almost impossible, but what we call that one simply is going to be a sugar. And in fact, we called it glucose. So some of them will have special names for them as well. Okay, well that's it for this video. Good luck in the lessons, and we'll see you in the next video. Okay, so we're going to start off with a real quick talk about the molecular structure of water. If you look down here below, what you'll notice is that molecule of water that we recognized when we were talking about covalent bonds. And in covalent bonds, remember, they share the electrons. So between our hydrogen and our oxygen, we have these shared electrons. Now, even though they're sharing, these electrons are going to spend a little bit more time down here on the oxygen atom than the hydrogen atom. And as such, that results in a slightly positive charge on the hydrogen atoms here. Because the electron's a little bit more away and that proton's exposed, it gives it a slightly positive charge. Now, because these electrons are spending a little more time down around here, orbiting around the oxygen atom, it gives us a slightly negative charge down here. And because we have a positive on one side and a negative on the other side, we call that a polar molecule. And polar molecules are kind of neat because they are able to pull apart ionic compounds, but also it sets us up for what we call hydrogen bonding. So because this hydrogen is slightly positive and this oxygen is slightly negative. In nature, remember, opposites attract, and those two are going to kind of hold on to each other in a weak bond. But if we get enough of them there, then we can kind of see how water has some unique properties because of this. So because water has a unique formula, it gives it a bunch of unique properties as well. One of them is this idea of large capacity to hold heat. What that means is it takes a little bit more energy to heat up the water molecules and make them to move apart, so they store that heat energy there, but then they also take a longer time to come back down in temperature. So that works a lot of times as a buffer, or it keeps the milder conditions. So if you lived on an island surrounded by water, you would notice there weren't such drastic temperatures, and that can make for a milder climate. Now, the reason is because of these hydrogen bonds, which we talked about in the earlier slide, so we don't need to go through that one. But this one here is key, is the fact that water expands as it freezes. In fact, at about 3 degrees centigrade, water expands real quickly. What makes that unique is that means that the solid version of water, or ice, has a lower density than the liquid form, which is the water. And that plays an important part if we think about like a pond or something of that nature. If that pond is sitting there and it has water here, and then in the wintertime it freezes, what it does is only the top part of the pond will freeze over and form ice. And that means that the little fishes down below are able to survive through the winter. And that's kind of a really interesting thing. And that works out really nicely. And you can try that on your own. Take a bottle of water and then stick it in the freezer, and you'll see that the bottle misshapes because of the pressure of that expanding water. And then finally, we talk about water being a solvent, and that means a lot of things like to dissolve into it. We're going to cover these two words quite a bit. This philic here means that it loves it, and this hydro means water. So these ones here are water lovers. Okay, and that means those are compounds that are going to love to dissolve into water, things like sugar, things like salt, things of that nature. We can also have a phobic, which is a fear of water, and these ones here are water haters, and those would be things like oils that just don't dissolve in water at all. Okay, well that's it for water. Good luck with the lessons, and we'll see you in the next video. Okay, first up, let's talk about acids real quickly. Acids are substances that donate a hydrogen ion, or they can accept an electron pair. Some common examples for us to think about are stomach acid. Some of the other ones you've probably heard of: hydrochloric acid or sulfuric acid. Notice they have this extra H here, and that's kind of the clue that gives us the idea that it's an acid. Now, bases are about the exact opposite of acids. Acid could donate a hydrogen ion, a base will accept this hydrogen ion, or it can release this hydroxide ion. Okay, notice it has a negative charge. They also can donate an electron pair, and they're often referred to as alkali. Some common bases, the biggest one of all is sodium hydroxide, and you'll notice it has this OH, this hydroxide group in the name, and that kind of gives us a little clue that it's a base. Okay, so let's look at the differences between acids and bases. Remember that they are opposite of each other. So for an acid's going to accept an electron. A base, on the other hand, will donate an electron. An acid donates a proton. The base will accept that proton. Okay, acids generally tend to break apart into this hydrogen ion, while our bases form these hydroxide ions. And you can see some examples over here. We talked a little bit about lemon juice. Our stomach acids are filled with our nucleic acids or acids down here. And then we talked a little bit about bases. We talked about sodium hydroxide, then baking soda would be another one here. Okay, so if we want to see how strong or weak an acid or a base is, we use something called the pH scale. The pH scale runs from 0 to 14, and right here in the middle is where we have something that is neutral. Okay, and that's going to have a pH of 7. And the best example we have of neutrality is this one right here, this pure water. Now remember, if we look at the idea of water and its formula, it is a hydrogen, which we said makes an acid, and it is a hydroxide, which makes a base. So you add those together and we end up with something neutral, which kind of makes sense to us here. Okay, and as I alluded to, we have our acids. Our acids range from 0 up to 7. Remember, at 7 it's neutral, so it's not quite there. And some examples, like we said, stomach acid is a pretty strong acid, vinegar is one here, and even what comes out of our tap water tends to be slightly acidic. Now our bases are going to have a pH greater than 7. Okay, so these ones here are going to be greater than 7, and things like our soaps are going to be 1, and then lye is a real strong one here. We talked about sodium hydroxide. Okay, so our pH scale goes from 0 to 14. Those with numbers lower than 7 are going to be acids, and those with numbers greater than 7 are going to be bases. Okay, the last topic we're going to talk about today are going to be buffers. What a buffer does is it kind of restores neutrality to a weak acid or a weak base. And that's going to be really important if things like blood, where blood wants to be about neutral. So if it gets too acidic, we can die, and if it gets too basic, we can die. And it doesn't have to get very far. What a buffer does is we add it into our solution, and then what it'll do is it'll kind of break apart the acids and the bases, and they'll form a little bit more of these waters, and that just kind of dilutes it down and makes it more neutral. So key thing, we use a lot of buffers when we're talking about biology, and we'll go through those just a little bit, and they'll go through them a little bit more in the lesson. Okay, that takes us to the end of our video today. Hopefully you learned a lot. Good luck on the lessons, and we'll see you next time.